On June 22nd of this year, a paper landed in the journal Nature that quietly confirmed something genuinely strange about the visitor that passed through our solar system last year. A finding that took the better part of a year of careful analysis to reach publication. Researchers at NASA Goddard, using the James Webb Space Telescope, measured the ratio of methane to water pouring off comet 3IATLAS, and the number that came back was roughly 11 times higher than anything ever recorded on a comet native to our own solar system. Not 11% higher, 11 times higher. That is not a rounding error, and it is not a measurement glitch. It is a real, peer-reviewed, published data point about an object that formed before our sun existed, and it is the honest starting point for tonight's deep dive, because you do not need a single invented detail to make this story remarkable. The real data already is. 3IATLAS is the third confirmed interstellar object ever detected passing through our solar system, following the strange, tumbling visit of Oumuamua in 2017 and the far more ordinary cometary body Borisov in 2019. Those first two visitors are worth understanding properly because they set the entire scientific baseline against which 3IATLAS gets measured. Oumuamua showed no detectable coma and no visible tail at all, an object that appeared to be bare rock or ice with no active outgassing. Yet its brightness varied by roughly a factor of 10 as it tumbled through space, a variation so extreme that researchers concluded it had to be unusually elongated, shaped more like a flattened plate or a cigar than any asteroid or comet previously catalogued anywhere. It also displayed a small but measurable non-gravitational acceleration as it departed our solar system, a subtle extra push beyond what the sun's gravity alone could account for, most commonly attributed by researchers to outgassing of hydrogen too faint for contemporary instruments to detect directly. Borisov, arriving 2 years later, was in almost every sense the opposite case. It behaved like a textbook comet, actively venting familiar volatile gases on a curve that matched standard cometary models closely. Though even Borisov carried one genuine surprise of its own, an unusually high concentration of carbon monoxide relative to water in its coma, suggesting it may have formed in an especially cold region of its home system. 3IATLAS sits in a genuinely new position relative to both of these precedents. It is active enough to produce a real, substantial, well-studied coma, the way Borisov did, but the specific chemistry inside that coma, the extreme methane enrichment, and the extreme deuterium signature has no precedent in either of the two prior interstellar visitors, or in any comet ever measured from our own solar system. It was first spotted on July 1, 2025, by the Atlas Survey Telescope in Rio Hurtado, Chile, a facility built and funded specifically to watch for exactly this kind of fast-moving, unexpected object as part of a broader planetary defense network. Within days, astronomers had gathered pre-discovery observations from archived data captured by other Atlas telescopes around the world and by Caltech's Zwicky Transient Facility at Palomar Observatory, extending the confirmed observational record back to June 14th, weeks before the object was formally identified. This is a completely standard and transparent practice in astronomy. Once a new object is flagged, researchers routinely comb through existing survey archives to extend its known observational history. And it is exactly what happened here, openly and rapidly, with the results published for anyone to review. Astronomers confirmed within days what its trajectory was already screaming. This object was moving on a hyperbolic path, meaning its velocity relative to the Sun exceeds the threshold required for the Sun's gravity to ever capture it into a closed orbit. Every orbit in astronomy comes down to a balance between an object's velocity and the strength of the gravitational pull acting on it. If an object moves slower than the local escape velocity, gravity wins, and the object is bound permanently into a closed loop, an ellipse, destined to return again and again. If an object moves faster than escape velocity, gravity can only bend its path, never close it into a repeating shape, producing a hyperbola, a curve that swings past its central body exactly once before departing forever along a trajectory that never comes back. Every comet ever catalogued before Oumuamua's discovery in 2017 showed velocities and trajectories consistent with a closed, if sometimes extremely long, elliptical orbit. 3IATLAS's measured velocity and trajectory placed it unambiguously on the hyperbolic side of that line, and by a wide enough margin that no measurement uncertainty or gravitational perturbation from a planet could plausibly explain it away. Every planet, asteroid, and periodic comet native to our solar system loops around the Sun on a repeating ellipse. 3IATLAS does not. It came in on a single open arc, and it is now leaving permanently, never to return. That single measured fact is the entire, uncontested proof that this object did not form here. It came from another star system entirely. To understand why that matters so much for the chemistry findings, you have to understand what a comet's coma actually is. The solid nucleus at a comet's center, typically a mixture of frozen water, carbon dioxide, carbon monoxide, and other volatile ices bound together with dust and rock, is usually too small and too dark to see directly. What telescopes actually observe is the coma, a vast, diffuse cloud of gas and dust released when solar heating vaporizes those surface ices, carrying trapped dust particles out into space along with the escaping gas. By passing the light reflected and emitted from that coma through a spectrograph, an instrument that spreads light out by wavelength the way a prism spreads sunlight into a rainbow, researchers can measure the precise chemical composition of the material boiling off the nucleus. Because every molecule absorbs and emits light only at specific wavelengths determined by its own unique atomic structure. This is exactly how the James Webb Space Telescope measured that methane-to-water ratio, and it is why the finding is considered a hard data point rather than a matter of interpretation. Methane is what is known as a hypervolatile ice, meaning it sublimates, turns directly from solid to gas at extremely low temperatures, far lower than water ice requires. A comet releasing this much methane relative to water is releasing a coma dramatically enriched in one of the most fragile, easily lost ices there is, and doing so at a level nobody has recorded on any comet that formed around our own sun dot. That finding did not arrive in isolation. In May of this year, a separate team, publishing in Nature Astronomy and led by researchers at the University of Michigan, measured something else entirely inside 3IATLAS's coma: the ratio of deuterium to ordinary hydrogen within its water molecules, commonly referred to as heavy water content. Deuterium is a naturally occurring isotope of hydrogen, an atom with an extra neutron in its nucleus, and the ratio between it and standard hydrogen inside a body's water ice acts almost like a chemical fingerprint of the specific environment and temperature conditions present at the moment that ice originally formed. The heavy water content measured in 3IATLAS came back astonishingly high, far exceeding anything seen in comets, asteroids, or any other icy body cataloged in our own solar system. Taken together, an extreme methane to water ratio and an extreme deuterium signature, this is not one anomaly, it is two independent, separately measured, separately published chemical signatures, both pointing toward the same underlying conclusion. The ice inside this comet formed under conditions colder and chemically stranger than anything our own solar system's formation history ever produced. This is where the mission history of the object becomes genuinely fascinating, because 3IATLAS did not simply drift past unnoticed. It became the most heavily observed interstellar object in history, almost by accident of good timing, watched by the Vera C. Rubin Observatory during its science validation phase, by the Hubble and James Webb Space Telescopes, by NASA's TESS satellite, by the Perseverance rover and orbiters at Mars, and by an entire fleet of spacecraft already positioned throughout the inner solar system for entirely different missions. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, had completed a Venus gravity assist maneuver earlier that year and happened to be positioned in deep space at a distance of roughly 0.428 astronomical units from 3IATLAS in early November of 2025, an extraordinarily useful vantage point that no ground-based telescope on Earth could match. JUICE turned its cameras, spectrometers, and particle sensors toward the object, capturing real observational data during a period when the comet was highly active. The spacecraft's science camera, a more capable instrument than the navigation camera used for the initial quick look, returned imagery showing a cleared tail and visible structure within the coma once the fuller data set arrived. Its spectrometer suite is designed to measure composition across visible and infrared wavelengths, the same basic principle used by JWST to detect the methane and water signatures, giving researchers an independent, closer-range data set to cross-check against the Space Telescope findings. The particle sensor aboard JUICE measures the actual physical environment around the spacecraft directly, ions and electrons in the surrounding space, data that can reveal whether and how the comet's outgassing interacts with the solar winds streaming past it, a genuinely useful complement to the purely optical and spectroscopic measurements taken from telescopes. Because of the sheer distance involved and the limits of deep space communication bandwidth, only a partial navigation camera image could be quickly downloaded at first, confirming an active, structured comet with a visible tail. The bulk of JUICE's actual science data did not finish arriving back at Earth until February of this year, and instrument teams are still working through the full analysis. That is not a cover-up. That is simply how deep space missions work. Data transmission from beyond Jupiter is slow, bandwidth limited, and prioritized carefully, and a spacecraft's primary mission, in this case eventually reaching Jupiter's icy moons, always takes communication priority over a bonus target of opportunity like this comet dot. Other spacecraft got their own look as well. NASA's Europa Clipper, on its own outbound trajectory toward Jupiter's icy moon Europa, captured rare ultraviolet observations of the comet in December of 2025, at a moment when ground-based telescopes on Earth were still blinded by the sun's glare, a genuinely lucky piece of orbital timing that let a spacecraft designed for an entirely different mission make a real scientific contribution to this one almost by accident. Mars orbiters, including ESA's Mars Express and ExoMars Trace Gas Orbiter, observed the comet in early October as it passed within about 29 million kilometers of Mars, close enough for multiple instruments already stationed there to get a genuine, if distant, look. And those observations were later used to help refine estimates of the comet's precise trajectory. This was, quite simply, the most thoroughly observed interstellar visitor in the short history of interstellar object science, watched by an entire fleet of spacecraft that happened to already be in the right places at the right times. The object reached its closest approach to the Sun on October 30th, 2025, at a distance of about 1.4 astronomical units, just inside the orbit of Mars, and it survived that passage intact. This matters more than it might initially seem, because a smaller or more fragile object could plausibly have broken apart under the thermal stress of close solar heating, the way some sun-grazing comets from our own solar system do. 3IATLAS held together, continuing to actively vent gas and dust in a coma bright enough for Hubble to resolve clear structural detail. Early size estimates from Hubble observations in July and August of 2025 placed the nucleus diameter somewhere between roughly 440 meters and 5.6 kilometers, a wide range reflecting the difficulty of separating a small solid nucleus from the much larger, brighter coma surrounding it. Later analysis using post-perihelion Hubble data that allowed researchers to better isolate the nucleus from the coma's glow refined that estimate to an effective diameter of approximately 2.6 kilometers, making it a meaningfully larger body than Borisov, the second interstellar visitor, and placing real physical scale behind an object whose chemistry keeps returning numbers nobody has seen before. It is worth explaining exactly why researchers can say with such confidence that this hyperbolic trajectory is real and not some kind of gravitational fluke involving an unlucky slingshot past a planet. 3IATLAS did not pass close enough to Jupiter, Saturn, or any other planet in our solar system to have had its trajectory altered or its speed boosted by a gravity assist on the way in. Its speed and direction were essentially fixed before it ever entered our solar system's gravitational influence. Astronomers ran the numbers and found that this object could not have originated from anywhere within our own solar system under any physically plausible scenario. It had to have arrived from interstellar space, already moving at the speed and on the trajectory researchers measured, meaning everything about it, its ices, its dust, its isotopic ratios, is a direct sample of material formed around an entirely different star, transported across the galaxy over what researchers estimate to be somewhere on the order of billions of years of travel time through the emptiness between star systems. Now, it is worth being completely honest about the parts of this story that get exaggerated online, because there is a real difference between confirmed science and speculation dressed up to look like it. Harvard astrophysicist Avi Loeb has published an extensive, well-publicized list of what he calls anomalies associated with 3IATLAS, including claims about the alignment of its trajectory with the plane of the planets, a small non-gravitational acceleration attributed to unusual jet activity, and speculative scenarios involving artificial origin, up to and including the idea that the object's path could have been deliberately engineered to pass close to Mars and Jupiter while remaining hidden from Earth-based telescopes during its closest approach to the Sun. These are Loeb's own individually authored hypotheses, published primarily through his personal writing rather than through the standard peer review process most other findings in this story went through. And he has been direct about this himself, stating in his own writing that the most likely outcome is that 3IATLAS is a completely natural interstellar object, most probably a comet, while describing the more exotic scenarios as an interesting exercise worth exploring, regardless of their likely validity. Other researchers in the field have pushed back directly, with astronomer Samantha Lawler noting that extraordinary claims require extraordinary evidence, and that the evidence actually presented falls well short of that bar. A dedicated technosignature search conducted using the Allen Telescope Array, published in the Astronomical Journal by Sophia Sheikh and colleagues, sifted through tens of millions of individual radio signals during the object's passage and found 0 technosignatures consistent with any kind of artificial transmission. It is worth briefly explaining what a technosignature search actually looks for, because the concept itself is legitimate mainstream science rather than fringe speculation, and it has a long, respectable history in astronomy going back decades. Natural astrophysical emissions tend to spread energy broadly across a wide range of radio frequencies, essentially cosmic static, while any engineered transmission system tends to concentrate energy into a narrow, specific frequency band, the radio equivalent of a laser rather than a floodlight. Searching for narrowband signals against a background of broadband noise is a completely standard verification step in modern astronomy, and a clean, null result across tens of millions of signals, as researchers found here, is itself a meaningful, publishable scientific outcome, ruling out an entire category of possibilities with real statistical confidence. The scientific consensus from NASA and the overwhelming majority of astronomers actively working on this object remains that 3IATLAS is a completely natural interstellar comet. It is simply, provably, a very strange one, carrying chemistry that does not match anything our own solar system ever produced. Where is the object right now? As of the most recent tracking data, 3IATLAS sits at a distance of roughly 1 billion kilometers from the Sun, well beyond Jupiter's orbit, having passed within about 53 million kilometers of the giant planet in mid-March of this year. A close approach, but not any kind of engineered rendezvous, simply the geometry of its outbound path. It is continuing to recede permanently at a speed of roughly 246,000 kilometers per hour, the same speed it carried on the way in, meaning nothing about its passage through our solar system changed its fundamental trajectory or velocity. Interestingly, its brightness on the way out has actually been measured as somewhat elevated compared to its brightness on the way in at the same distance, a real, documented effect attributed to the excess dust and gas it continued shedding after its close solar passage, the aftermath of genuine, ordinary cometary activity rather than anything requiring an exotic explanation. What makes this story worth telling honestly, without embellishment, is that the real science already clears the bar for genuine wonder. An object formed around a star that was likely already ancient before our own sun ignited, carrying ice chemistry unlike anything in our cosmic neighborhood, survived a close pass by our sun, was observed by an entire fleet of spacecraft that happened to be perfectly positioned by coincidence, and is now continuing outward into the galaxy, carrying data that 2 separate peer-reviewed research teams are still working through. Instrument teams working with JUICE's full dataset, downloaded only months ago, are almost certainly going to publish further findings as that analysis continues. And given how much of the picture has already shifted meaningfully between last year's early estimates and this year's confirmed measurements, it would not be surprising if more genuine, verified anomalies surface in the coming months, not because anyone is hiding anything, but because deep space science moves on the timeline of careful peer review, not the timeline of a news cycle. 3IATLAS will not pass this way again. Whatever else its full dataset eventually reveals, the object generating that data is already 1 billion kilometers away and picking up distance every single day, carrying with it the only physical sample of another star system's chemistry that has ever passed close enough for our spacecraft to actually touch with their instruments. Every measurement made of this object, from Chile to Baltimore to the instrument teams working through JUICE's data right now, will remain the only direct data humanity has on the chemistry of a world that formed around a star we will likely never even identify by name. There will not be a fourth close pass, a follow-up mission, or a second chance to point a better instrument at it once something is missed. Everything worth learning from 3IATLAS has to be learned from the data already collected, in the archives, in the published papers, and in whatever comes out of the ongoing analysis over the months ahead. That is the real story. It does not need anything invented to be worth paying attention to.